Hello, my name is Wayne Kaplan. I'm a professor in the Department of Materials Science and Engineering here at the Technion, and I'd like to briefly introduce the research topics that my group is working on. We're focusing on interfaces, specifically metal-ceramic interfaces, and trying to understand the physics and the engineering behind them. Basically, when we talk about interfaces between materials, we're talking about a planar point of contact, and there are two main ways to discern or to study what's happening there. One is the continuum approach, and the other is the atomistic approach. In the continuum approach, we can talk about wetting, which is the relative surface to interface energies of the system, and adhesion, and at the atomistic approach, trying to understand the atomistic structure which lies behind the adhesion. This also includes the topic of absorption and the motion of dopants to surfaces, which again change the surface energy and then affect adhesion. And then in recent years, we're focusing on grain boundary kinetics. Some specific examples. On the left, you can see high temperature wetting experiments where we're looking at the contact angle of, in this case, a liquid on a solid at high temperature. But we also look at wetting of solids on solids to measure interface energy and adhesion. And we can correlate this to the atomistic scale. On the right, you see a brief movie showing high-resolution TEM images of the interface between liquid aluminum and sapphire. And at the interface, in the liquid atoms are not disordered. They're very, very ordered. That's what we were able to discern, indicating that we have a two-dimensional material which is neither a liquid nor a solid. It's something in between. This actually brings us right into the topic of adsorption, which is also a major topic of research, where we're looking how dopants adsorb to interfaces, alter or reduce the interface energy, and therefore affect adhesion. Of course, the atomistic orientation of the dopant species and how they change the interface itself has to be addressed, and that's done on the atomic scale. And then finally, as I mentioned, we're looking recently at grain boundary mobility. The size of grains and polycrystalline material is the basics to materials engineering. So we're, on one hand, measuring the normalized velocity of grain growth, and on the other hand, correlating it to the mechanism, again, using advanced atomic resolution, high resolution TEM electron microscopy to look at the atomic structure at grain boundaries in order to study the mechanism by which grain boundaries move. Atoms don't just hop from one side of the grain boundary to the other. There's a specific mechanism correlated to the kinetics and the thermodynamics of the system. Obviously, none of this can be done without advanced electron microscopy, something that my group uses a lot of, and luckily here at the Technion, we are very, very well facilitated with the best electron microscopes available. If you want more information about what we do, I invite you to take a look at my website. You'll find full description of the activities and the people, and you can reach out and contact me.